Yeah, yeah.
Okay, we're going to start in on displacements and strain as we crawl our way towards stress.
Microphone?
Is it not on?
No.
I think it's on. It should be. Yeah. Yeah. That's
You're
right.
okay, Ross. We're ready to go.
You know, I noticed when I'm standing behind everybody, it's really great because you see all these same things on the screen, and it's like we're at the NASA, Houston Center monitoring the progress of the Apollo mission or something. Okay, where we are in the manual now is page 27, which is the start of the deformation chapter. If you quit out of Coulomb, relaunch the program by writing the word Coulomb in the MATLAB command line. But if you didn't quit out on it, it should still be there. And if you're like Shinji is, you're in Cartesian coordinates, which is good, which is where I'd like you to be for this. And what I'd like you to do is to go to the input menu and choose Open Existing Input File, and choose that trusty example2 LL file. Example2 parens LL, left lateral fault. And so just say OK for that guy. Example2 LL, an existing input file, and you should get this. Now, because we're going to plot displacement vectors, and it'd be awfully dense if we did it with these kind of increments. So let's change the grid spacing by go to Functions, Change Parameters. Shinji Functions, Change Parameters, and change grid size. All right? And change it from to 5 by 5 kilometers. It's good exercise anyway. And now, when you say OK, yeah, you'll need now to go back to Functions, Grid 2D Map View. OK, so you have that on your screen, right? Maybe that's a little not quite dense enough. Well, all right, let's try it. Let's try it. So we're going to go to Functions, and then we're going to go Displacements, horizontal displacement, parentheses, vectors. Okay. And you should see something that looks like that. Now, there's two things that are really, really useful to do here. And the first one, see the dialog box in the upper right, which is the displacement control dialog box? See how it has reference no fixed point. That means that the reference point is kind of infinitely far off in space. So, for example, you get equal and opposite displacements in the middle of the fault that are consistent with a left lateral fault. But what's really interesting is to choose the fixed point. So go and click that radio button, and then click on mouse click. So now if Shinji goes to go down to the other side, or go a little closer to the fault to where you go back where you were, kind of in the middle, or go up, keep going up, a little to the right, about one's grid box. Yeah. Okay, now click there. And so now you get this very different pattern with the exact same displacement field because you have a different vantage point, and you even get this kind of vortex occurring. So just for fun, try it again and put it wherever you want. And this is relevant to the issue of when you have a set of GPS observations and you're holding one of those stations fixed, but it's also a wonderful teaching tool to tell you something about how the displacement field around a fault works. Why don't you do very close to the fault near the, how about like right there? Yeah. Yeah, so then it's really, really interesting just to do this. And you get to see this, and you also notice that these vectors have a scale bar in the lower left-hand corner to tell you what they are. Now, I want to introduce to you the other part of the displacement control panel, and see how it has a number down there, 10,000? That number has a meaning, which means you can see that what 10 kilometers is on this map, and that 1 meter of displacement is exaggerated 10,000 times. So it has a very specific meaning. It's not a relative term. But why don't you just use the slider and slide it so you change that, or then make it really small. So that's also very, very useful for you to very quickly find the scale that's kind of naturally and intuitively appropriate for the plot. If you use too big, they tend to wash over each other. And you can, at some point, if you import this file into Illustrator, you can select all those vectors by their stroke and fill and do something to them, but you probably won't need to do much because they already are pretty good. Now, also notice that the depth is shown there, and depth is 7.5 kilometers because we're usually thinking of the depth at which some stresses are being calculated. But for displacements, we probably, if we're thinking of GPS displacements at the Earth's surface, you probably want to change that to 0. So Shinji, why don't you just change that to 0? In this case, it won't look that much different, but if we were to choose a thrust fault, it would look very, very different. Yeah, it looks kind of the same here because for a vertical strike-slip fault, there's not a very strong change of displacement with depth, but other faults would have a rather profoundly different one. Now, another thing you can do is, like all files, this automatically produces a numerical output file. And that file is called displacement.cou. I don't want to spend time on it, except if you just look on page 27 in your manual, in the lower left-hand corner, it just shows you what files these kind of files look like. So just know that any time you make a calculation, you can always grab and rename the numerical output file so you can have that and you can plot that in your own program. Yes? It is going to be in which? It's the output files folder. Thank you, Volkan. Yes. You can see that. Yeah, you can see on the command line every time Shinji made a change, it printed out that it had produced a file. So if he had wanted to save one, he could have. Now, is all he was doing is changing the relative position. So in fact, the output file would look the same because what he's doing is just different graphical representations of it. That numerical file is the XY position, XYZ position of all those vectors and their lengths, their XYZ vector. So it's not the relative values. So now you can also make cross sections. And to do that, we're going to go to Input, Open Existing Input File, and we're going to choose that thrust case because that'll look more interesting in cross section. So we're going to example 2TH. I know we have a kind of a slavish devotion to a couple of files here. It's completely inexcusable. And so now what we're going to do is functions, displacement, horizontal displacement, vectors as we did before. All right. And that's kind of interesting. And now on the displacement control panel, you can see that there is a button that we didn't look at before called cross-section. Does everybody have that? So click on cross-section. Now, this input file happened to have a cross-section identified in it already. But you can see that once you've done that, a new panel opens up, cross-section control panel. So you could either with mouth clicks or with numbers put in whatever you want. But here's what I want you to see in that cross-section control panel. It has the horizontal increment and a depth increment. So let's make that 2 by 2. The meaning of depth is that's the lower depth of the calculation. It automatically starts at 0 and goes down to whatever lower depth you put in. And 2 by 2, I think we're looking at about 2.5 there. So now we're going to say calc and view. Is everybody with us? And there it is. So if you don't see that on your screen, just put your hand up, and we'll give you a massage. You wish. Okay. So it's kind of a... What?
Scale.
Yeah, and now let's just change the scale. Let's exaggerate the scale a little bit. Not too extreme. Yeah, all right, that's perfect. Now, one of the things you see here that's really interesting is that you can see how asymmetrical the displacements are. On the up-thrown side, you see much more uplift, and on the down-thrown side, you see very little. And this is a free surface effect. What Steve Ward showed in a paper about 12 years ago is that a 45-degree dipping thrust fault has the maximum amount of uplift with respect to downdraw. And a 45-degree dipping normal fault has the reverse. It's mostly subsidence and very little uplift. And a horizontal fault or a vertical fault has exactly symmetrical uplift and subsidence. And you could, in Coulomb, very quickly take this fault, and as you bury it deeper and deeper until its depth is much larger than its width, you will see that those displacements will become perfectly symmetrical. So it's completely a free surface effect, and it's affected by the Poisson's ratio. Remember the Poisson's ratio, if I start with a square and I squeeze it this way, it's whether or not if it comes out exactly the same amount in the other direction, that's a Poisson's ratio of 1/2. That's like an incompressible fluid, whereas most elastic solids, and we tend to assume the Earth looks like this, if you push it this way by a factor of 1, it only goes up by a factor of 1/2. That's a Poisson's ratio of 1/4. That's the default setting in Coulomb, but you can obviously change it. So I'm thinking here of teaching structural geology and teaching displacement. You could easily use this to illustrate to students what the effect is of a blind fault versus a surface fault, a normal or reverse fault versus a strike-slip fault. And you could make any of these cross-sections what the geologists call retrodeformable, which means they conserve cross-sectional area just by changing Poisson's ratio to 0.5. So for example, if Shinji went to functions, change parameters, do we change, can we change Poisson's? Yeah, all input parameters. So if we change Poisson's ratio to 0.5 there, you don't have to do this, but we'll just see if there's any noticeable effect. And now Shinji does the same thing, displacements, horizontal displacement vectors, cross-section, 2 by 2.
Oh, I changed that.
The differences are too subtle for me to see. But I promise you, the value of this is geologists make a big deal out of it, retrodeformable cross-section. That means they could take those cross-sectional areas and deform it back before the faulting started. In an elastic world, some areas get compressed and some areas get extended, and there's no requirement that it's retrodeformable. And this is a simple way in Coulomb we can do it.
Is there a way of showing two files at once, two images at once?
No. So what you would have to do, the way you would do that is two ways. You can make a screenshot and put that up. You know, in the Mac world, that's just a couple of keystrokes. Or you could save it as a PDF file and then have it up in Acrobat. But you don't get to have two things up at once. You only get a cross-section and a map view at once.
And then this dash line is...
Oh, and the meaning of the dash line, Shinji wants me to remind or tell you, is that's the depth in the map view. So that's kind of nice that you can relate the two that way, because it's telling you where your depth was chosen for that. Now let's do something that would be a little bit more friendly to a geologist, which is we're going to go functions, displacement, horizontal displacement, wireframe. Are you there? Okay. Wireframe. And let's look at that cross-section again. click on the cross-section, make it 2 by 2.
Mouse wheel?
No, we'll keep it there, but let's go 2 by 2. Okay. Calc and view. And now why don't you zoom in there, Shinji? Actually, no, you can leave it the way it was. You made it. So now is all you'd have to do is take that into Illustrator or something, and you could color these as strata. And then you're starting to illustrate the deformation we would expect from continued displacement on a reverse fault, for example. So now it starts to become very relatable to what a structural geologist sees. And it...
Go ahead.
What do you want to do?
Brian.
Okay, so now Shinji is going to make it a blind fault.
Oops.
So he's going to do horizontal displacement wireframe again. Oh, that's very nice. And so now you're seeing this. This is wonderful that you did this. Now we have an anticline, a very gently dipping anticline over the fault. We have offsets below. You can see the fault is in red there. And so now we're seeing how an anticline grows over a fault and the features of that, which is that the zero crossing where the anticline goes through the undeformed surface is exactly where the projection of that fault comes to the surface. Why don't you just put your mouse on that point?
What?
Yeah, that's the projection. The top of the anticline is right over the top of the fault. That's where the peak uplift is. And you could start to change the dip of the fault and see how the asymmetries change. So if this was a very 30-degree dipping fault, then the syncline, the downdrop side near the B, would be relatively larger compared to the anticline. So what we're thinking here is that this is a wonderful way to expose people to some parts of structural geology and elastic dislocation theory. And it's a lot more intuitive than just looking at the equations. It's also interesting to see way down at 25, 30 kilometers, there's still quite a bit of deformation associated with this upper crustal feature. And so presumably, in a long-term sense, this is what's promoting viscoelastic response, which is something that is not included in Coulomb, but you can see the motivation for it. So now Shinji is going to look at another view and how easy it is to look at different views. And Shinji has done this such that even if your A and B cross over a corner of the fault, you'll see that corner of the fault projected in the cross-section map. And let's go back to the map view for a moment. So obviously that has too much exaggeration. It's kind of hard to understand what you're seeing. So why don't you remove the exaggeration, or quite a bit of it, in the map view. So change that from 10, yeah. Yeah. So this is kind of the torn nylon view of the world, or view of structural geology, but it's pretty useful. And some other very nice ways of visualizing deformation are available. Let's open that left lateral file again. So we're going to go to Input, Input, Open Existing File, and we're going to do left lateral, example 2 LL. Go up one, yeah. All right, now we'll leave that grid spacing and we'll go up to Functions, Displacements, and we're going to go now to Vertical Displacement, Color, and Contours. Vertical Displacement, Color, and Contours. Okay? Okay, so now you can see that this is the vertical displacement at a particular depth, and this is at 7.5 kilometers. No, yeah, at 7.5 kilometers. So this is a surface. It's not the free surface. It's not the Earth's surface. It's about halfway down the fault. And I want you to see a couple of things. See where it says in that vertical displacement control panel, tiled and interpolated? So click on interpolated. And you can see now you get a beautiful smooth file. One of the wonderful things about MATLAB is that this very nice smooth gradient file is a very, very small file. So this isn't going to tax your computer. Compared to Coulomb 2, these things used to be very big files, and these are nice small files. So, again, thinking in terms of, let's change the depth to be the surface. So we're going to go to change functions, change parameters, calculation depth. Yeah. And now we're going to change that to 0 to be the surface. And now we have to, remember when we do that, we have to redo the calculations. So displacement, vertical displacement, color and contours. And then again, we'll change it from that ugly mosaic to the beautiful interpolated. I don't care if it's inaccurate, I just want it to look good. And let's change the saturation too. So with the scalars, make it so there's a little less red and less blue. Okay, perfect. So now, again, thinking in terms of seeing for yourself or teaching to a student, that you can imagine that if this is a left lateral fault, these red zones are where material is forming a little hill, is a vertical uplift. And the blue zones are where there's a sag pond. In other words, where things have been pushed down. And successive earthquakes, if this were an isolated fault, would produce that kind of geomorphology. So it's a very easy way to give someone a sense for, well, how much it's expected to go up and down for the amount of slip that we have in the fault. If you wanted to know how much slip is in this input file, then what Shinji will do is just click on the green line for the fault, and we'll see that by just clicking up change parameters. We say, oh yeah, how much slip is in there? There's 3 meters of slip. So now you can just say OK to close that. So,
Yeah.
all right,
It's
we'll just
automatic.
run that again.
Maybe we should change that.
It's all right. So then you're quickly getting a sense of the amount of displacement you would expect for that. And then on contours, if you see that word contour in the control panel on the right there, you can click on that. Yeah, it's warning you that the contour takes time. We might as well do it. Personally, I hate contours. Contours are just ways to make a good-looking figure ugly. But, okay, some people, you see? Ugly. Okay, but there it is, contours. And also the other problem with contours is they draw your eye to 0, which is kind of really meaningless for what the figure really wants to do. So I'm not particularly thrilled with MATLAB contours, but since I don't like contours anyway, I don't care. But I just wanted to show you that they're there, and you can change the contour interval as you wish. Personally, the problem with the publication world is they've always made it so expensive to use color. But as we move toward PDFs, black and white is dead. Long live black and white. One other really nice kind of way to display this is go up to Functions menu again, Displacements, and now choose 3D Image Drape. Okay. That's interesting. And then let's exaggerate this image drape some more. So let's go Functions, Change Parameters, Vertical Exaggeration. Okay. And now let's change that to, what is that? It's 10,000. Let's make it 30,000. Yeah. Because we'd like our little uplift zones to look like the Eiffel Tower. 3D image drape again, now that we've changed that exaggeration. It's not that more exaggerated, but you can begin to see now it's more exaggerated. Yeah, and Shinji's doing just the right thing. You've got to try that. This is very, very fun. Kind of lifting up the hood on a. So I'm sure you can see this is a wonderful way to introduce these features to students or ourselves. I say students, but in reality, this is how I learn best, is being able to explore things easily like this visually. And I can convince myself there's a numerical file somewhere if I need to show it to someone, but really, I just want to play. There's one more of these kind of things. It's shown on the top of page 32, and that is called 3D image wireframe surface, which is just kind of a more translucent version of what you're seeing. So now I want to show you how to get GPS data into this so that you can look at observed vectors along with the predicted vectors. So what you'll do is go to page 28. You'll see a little piece of a numerical file there, which is the format we're using for GPS data. Very simple, long lat, and the easting, northing, and upward direction, or if you like, the east displacement, north displacement, and vertical displacement. And we're showing you how you can do that in Excel and get it into Coulomb. And Shinji, do you have the Nagata file?
I guess so.
We have a file that we've prepared, which is just kind of fun for you to look at.
This one?
Yeah. So you don't have it. This is from a Nagata Chuetsu earthquake that occurred in 2007. But before you add anything yet, just
This one.
yeah. Yeah, go ahead and open it again. I want to. What? Oh, they have it?
Yeah.
Oh, you do have it. I'm so sorry. Okay, Shinji's showing you do have it. Nagata Chuetsu Oki earthquake. So what you're doing is you're going to input files, open existing input file, Nagata Chuetsu, and this is an MAT file, so it's got all this wonderful stuff in it. The blue are the active faults, black is the coastline, and there's several fault sources that Shinji has included in it. Okay, now we're going to show you, do we have the GPS file in their folders too? I don't think so.
I guess.
But now, don't do anything yet. Go to Overlay, GPS Stations, the Overlay menu, then pull down to GPS Stations. We do have it?
Yeah.
Oh, great. Okay, so we have that. So now click OK for that. Now, these circles are not air ellipses. They're just the station locations. They're large circles so you can see them. But if Shinji blows up an area in there, you can see the observed and modeled vectors for this particular case. And in this case, observed is blue and modeled is red. So Coulomb is not an inversion program, but it does allow you to plot those data with a model. So if you have an inversion where you have a best model, you can plot it this way. Yes? Yes. And so to do that, we go to functions, right, Shinji? This is controlled by vertical displacement, by vertical...
Grid, wait, just a moment. Yeah, try that. Did you put the memo?
Think. Let's try vertical exaggeration. So let's try something large, very different.
It's not vertical exaggeration.
Yeah, let's just see if this works. Now we run it.
Which one?
Yeah, it did work. Okay, so let's do it again. So we're going to go to Functions, Change Parameters, Vertical Exaggeration. So we should relabel that. It shouldn't be vertical exaggeration. It should be displacement exaggeration. And that would be, because you're never going to find it that way, because that doesn't sound like it, does it? We have a bug every 15 minutes in this class, very reliably.
Just change which one?
So you can change it to, it's 30,000 now. You want it, well, I think theirs will be at 100,000. So if you, I don't know, change it to whatever you want, 50,000. And so that number has meaning again. That's, you're taking a meter of displacement, you're multiplying times 50,000, so it's going to be 5 kilometers long on the map. And if Shinji zooms out, you will see the scale bar. You want to do that? Now, there's kind of a weakness here is that the scale bar is for 1 meter of slip, which sometimes is too big for your box. If it's a little earthquake, like the little 5.4 we had a month ago. So we should subsequently fix this so that you can choose the legend vector length rather than having it default to 1 meter.
And then you can do some forward modeling, changing parameters like this, and for example, changing the slip assignment.
Oh, that's nice. Did you see what he was doing? So just forward modeling, you can just click on a fault, you can change the slip on it and see what it does. This is obviously not an inversion tool, but it still allows you to see what's important in your problem and what is really controlling the GPS vectors that you have. You know, at some point it would be really nice for us to get error ellipses and things like that in here too. But at the moment, this is what we've got in, and it still allows you to look at data sets of this kind.
Oops.
Okay, and the last thing I want to show you in this chapter is displaying strain. So let's go back to that simple open existing input file, and we'll go back to the latlon case, the example 2LL for left lateral. Okay, and if you're there, go functions, strain. And then it'll bring up a box, and it'll ask you what strain parameter of interest. And so let's try a dilatation. Because dilatation might be very relevant for something else you're doing. Maybe you're looking at how an earthquake will induce fluid flow. So you want to know what the pressure field looks like. Maybe you're going to grab that numerical output file and do something to it in relation to work that you're undertaking. And you can see the other components up there, EXX, EYY, etc. And again, you're looking at strain at a particular depth, and you can change that depth. You can interpolate it and change. You can see that the it's in units of 10 to the minus 5 here, and you could change that as you needed to. That'll be 0, exactly 0 for that component. Okay, so now Shinji's going to go right across. But this is beautiful. He's made a cross-section. And so here is a case in which, if you think of the fluid field around an earthquake, there's an enormous pressure gradient that's driving fluid from the red zone to the blue zone, places for where it's being, oh, I got it backwards. Blue zone is being compressed, and the red zone is being extended, so presumably water in cracks is being pushed down that gradient. That gradient is going to be much stronger than the gradient that goes from the blue end of the fault up to the upper red end of the fault. So, you know, if things like this are of interest to you, then this is a tool for seeing that. Okay, so we've taken a quick tour of the displacement capabilities of the program. How does that look so far? And so now we're going to launch into stress. Okay, everybody up? Yes. How did we get the cross-section up? Okay, so Shinji, close it and do it again. That's good. Anytime you have a question about when we haven't been clear, holler. That's exactly what we'd like to hear from you.
Just here.
See, dilatation cross-section. So it looks like, yeah.
And then you can change the position.
So the mouse clicks again allow you to change what cross-section. So actually,
for mouse click, you have to click left.
Right, left click. So Shinji, I don't have a pointer up here, but what I want you to do is go from here to here.
Oh, section?
Yeah. Does this thing have a laser? Yeah, I think it does have a laser.
Or maybe we should show the thrust for example.
Well, just because this one's up. Yeah. So that was the thing I was showing you before. That gradient is much, much lower than the other gradient. So presumably, if this is the earthquake you have and fluid flow is being driven, it's really being driven across the fault rather than parallel to the fault if it's motivated by these by these gradients. Okay, everybody stand up for a minute. You've accomplished displacement. So, you need to kind of get your shoulders working again. Oh, thank you. Okay, so now I want you to know you're 3/4 of the way through this program. So, and you're getting the feel. I think I went a lot faster on running around this time. I got the sense that people were with it because now you've got a little bit more muscle memory. You know where to go for those input files and those functions. And okay, get down. Getting out of control over there. Okay, now open your manual to page 34, and I want to talk just a bit about Coulomb stress measurements. And the simplest case, the one I show on top here, is the same one I showed in the slides, except I've just turned the boxes 90 degrees. But you're familiar with that one, the effect of the shear, normal, and regional stress. And as I said in the beginning of the talk, we're going to deal with basically 3 kinds of receiver faults, faults that receive stress. And those are ones that are in the input file that have no slip. So those are ones where we're just resolving the stress on those faults in their rake direction or any rake direction we choose, because often we don't know what their rake direction is. Or we will look at focal mechanism files where we have 2 different planes on which the Coulomb stress is different as long as friction isn't 0, which introduces some funky problems, and stress on a particular fault orientation that we choose. That's kind of assuming that the world is a kind of Venetian blinds of parallel faults. And finally, optimally oriented stress calculations, where we assume that there can be faults of all kinds in any particular spot, and we're going to find the fault on which the Coulomb stress is most positive. So at any point in space, there may be all kinds of faults, and we're going to find the one where it's most, where it brings everything closer to failure. Now, another thing to consider is that the shear stress on a fault depends on the source, its geometry and slip, and a receiver, its geometry and slip, including its rake, because we need to know which direction it's shearing. When it comes to the normal stress, or the clamping and unclamping, everything is the same for the source. But for clamping and unclamping, we don't care about the rake, because it's just perpendicular to the surface. So there's one less piece of information we need to know about the receiver fault when it comes to the effect of clamping and unclamping. Now, on the bottom of 34 is the calculation of the optimal planes. And essentially, all we're doing is at every point, we're finding that orientation on which the Coulomb stress is most read. And for that, we need to know something about the regional stress. And what we're doing here is we're no longer assuming we know the geometry of all the receiver faults. And instead, we're trading that information for something else, assuming we know something about the regional stress that drives this fault system. In here, the regional stress is represented by these blunt arrows on the perimeters of the map. And the difference is, if you look at the lower right picture versus the upper right picture, if we move far from the fault, they're the same. But as we get close to the fault, they're rather different. And that's because the regional stress is about the same size as the earthquake-driven stress close to the fault. So near the fault, we're finding big rotations. We're finding another orientation on which the Coulomb stress is positive. So for example, if it's a right lateral fault, any other right lateral fault right next to the main source is going to have its stress drop. But a left lateral fault parallel to that is going to have its stress increase. So there are rotations that come into play. And in the lower right-hand picture, you can see these white and barely black lines that represent the optimum planes. Now, the way to think about it is that the internal angle between this white and the black plane in this picture is controlled by the friction coefficient. If friction is 0, the two planes are orthogonal to each other. If we have a high amount of friction, the two planes become acute to each other. And those planes are oriented with respect to the principal stress compression. Now, that principal stress is a combination of the regional stress, which in Coulomb we assume is the same everywhere, and the stress change associated to the earthquake. If we get really far from the earthquake, all we're going to see is the effect of the regional stress. So if this is, no, that's invisible, isn't it? Okay, so here's the regional stress that we've learned from focal mechanisms or borehole breakouts or earthquake striae or whatever we have. And then with respect to that, we can have two planes like that. And those planes, their internal angle to each other is controlled by the friction coefficient, and their orientation is controlled by the direction of that regional compression axis. And so Coulomb just does the tensor addition here. It calculates how the earthquake has changed the stress, and it calculates a stress tensor for that. And then it adds that to the regional stress tensor, which is uniform, and it gets a new stress tensor, and then calculates the optimal planes to it. Now you say, why do we go through this bother? And the idea is that when we look at aftershocks, we don't know if they're very small, which means they're very abundant. We don't know what the focal mechanisms are. So we make a hypothesis that those aftershocks are going to occur at the location and depth and on the fault plane, which is brought most closely to failure. It's a hypothesis. We don't know if it's right, but it's a tool that allows us to look without having to know the nodal planes. And you can say, well, isn't it better just to deal with the aftershocks for which we have nodal plane information? Yes and no. First of all, that's always going to be a minority of the aftershocks. But also, we then have to suffer the yin-yang ambiguity of those focal mechanisms that we don't know which one it really is. So we're going to have to calculate both and think about estimating which one it is. So that's why this method is worth thinking about. If you look on the top of page 35, you can see a feature of this, which is that on the right-hand side, the regional stress is really high, or the earthquake stress drop is really low. So the ratio of the earthquake stress drop to the regional stress is here 1/10. And as a result, there's very little rotation of the earthquake stress tensor, and it looks just like if we had fixed the orientation parallel to the master fault. If we look on the left, we either have a very high stress drop earthquake or a very low regional stress, and now the fault lights up red, and you can see that the black lines near the fault are very rotated. So basically, it's right lateral, it's faults that have been highly rotated that are brought closer to failure. So these are factors that play a large role in the look of these.
Can I just clarify, even for the calculation of the optimal planes, it's not rock friction, it's the apparent friction, isn't it? It's not.
It's the apparent friction on the receiver faults that we're interested in.
It's poroelastic friction.
Yes, and so, you know, you can put in, we used to have kind of a Skempton's coefficient as a parameter in Coulomb, but it didn't really tell us anything. That you could basically experiment with having low or high friction and see what effect it has. But yes, it's the apparent friction on the receiver faults that you're really interested in here, not the source fault. So let's, with that as an introduction, to just give you an idea of the simpler kind of calculations and the little bit more complicated calculations of the optimal planes, we'll look at some cases. And the first one to start with is the one that 90% of Coulomb studies that you see in publication use, which is specified receiver faults. So now we're going to go to functions. and we're going to go to stress, and we're going to go to Coulomb stress change. We're not going to look at it, but you could look separately at normal and shear stress, but there's no real need in the class. Okay, and you get a stress control panel here. Now I want you to see that the first box is receiver faults, and you can see your choices are a specified faults, which means that's the Venetian blind world where all faults have the same geometry. And the second set of options are these optimal planes. What's important is that if you choose specified fault, it ignores the regional stress in your input file. Whether or not it's there or not, it's not going to use it, because all it needs to know is to resolve stresses on a particular plane. So let's start with that one. And let's choose, for strike, dip, and rake, we'll choose anything we want. Shinji, choose something. Okay. By the way, Coulomb automatically puts up strike, dip, and rake of the source input file. And if you have a whole bunch of source faults, it automatically puts up their average, which is kind of a nice starting zone if you feel that all the faults are kind of parallel, which works until you look at the Earth and the faults are never parallel. But anyway, it works in the Bay Area, but it doesn't work in Southern California. But you can choose what you want. So Shinji has put up 41, 90, and 0. And then choose Calc and View. All right, and let's change this to interpolating so it isn't so ugly. And it does that one on the fly. Okay, so there's the pattern. And I think you'll see this as kind of the traditional kind of expected pattern with the blowtorch zones along on the ends, those little offshoots on either side because of the impact of the normal stress change, and the big shadow zone in the middle. Now, let's say we were to change the friction coefficient to be 0. Then the dilatation and compression zones have no impact. And you'll see that this pattern will then become symmetrical. So change friction to 0. And now it's pretty symmetrical. The reason why it isn't perfectly symmetrical is because we're not resolving along faults exactly parallel to our source fault. Yes?
So where is the receiver fault?
Where is it?
Yeah.
Okay, so Shinji, click, and everybody, click on the word strike line over there. Great question.
Where?
See it over there to the right of friction? Okay, now click Calc and View. And so now it's put up the orientations that we've chosen. You can see they're not quite parallel to the main fault, and that's why it's not perfectly symmetrical turtle there. But it's close. Yeah. So those are the orientations that you happen to have chosen. Now, what's kind of fun is to click on the greater than sign in the upper right-hand corner of the stress control panel. And that produces sliders. So play with that. And every time you do that, it will change the stress pattern appropriately. You know, we've chosen a fairly high grid size. This would be faster calculation if we made the grid coarser before.
Something wrong with this.
Yeah, it didn't change the pattern, did it? Uh-oh.
I think we should refresh that.
Did you change the friction?
Huh?
You change the friction?
Yeah, we can change the friction, but we're a little nervous here that it's not changing the pattern like we expect.
It changes the pattern. It changes.
Oh, really? But it should also change by changing these parameters.
Yeah, you have to zero.
You had to close what?
I had to close the window.
Oh, really? That's great to know.
So you hit close, and then
She said she was able to do it once she hit close. Well, let's do it up. Let's do it there, not in the slider. Let's just change the parameter, Shinji, up there. That's not good. It should change both.
Mine's working fine.
Yours is working fine.
Why not? I don't know. Maybe just try again.
So just change that to 141 or something. All right. Yeah. That's more like it. Now, this produces a file that's created, an output, numerical output file, which just is a matrix of numbers. And so whenever you want that, if you want to bring that into another program or something, just remember to rename it. And you've seen how to do that. And it automatically is in the output folder. And it's the file name is dcff.cou. CFF is kind of a commonly used abbreviation for Coulomb failure function. Now, I'd like you to open page 37 in the manual. And just for you to see how these stress patterns are very dependent on the receiver fault orientation. So the figure here, which is reprinted from a paper of Jian and mine, shows a very highly schematic 1857 San Andreas earthquake. So when I say we always start simple, you can see how simple we start. It's just a straight magnitude 7.8 earthquake. And in panel A, we use a specified fault orientation that's parallel, that's the same as the main fault. So it's other vertical, north striking, strike-slip faults. And then you see the kind of the traditional view of the stress shadow, that blue-purple area. And we happen to have placed our secondary fault in a region where the stress is increased. And then if you look at B, you can see for this same earthquake on the same San Andreas fault, now we're asking, well, what is the stress on thrust faults that strike parallel but have a rake of what for a thrust fault? 90, yeah. And you can see that now it looks totally different than it did before. And now that little thrust fault is in a negative zone. And then in C, we do it for another thrust fault, but now it's striking 90 degrees rather than 0, and the pattern looks completely different again. And finally, in D, we do it for a left lateral fault. This is kind of a quasi-Garlock fault, and the pattern differs again. So it's just a reminder that people often talk about the San Andreas stress shadow or the 1906 stress shadow, but this is a highly abbreviated concept because in reality, it's only a stress shadow to you if you have a certain orientation, but for another fault of another orientation, it actually may be a trigger zone. So the idea of this panel is that you can quickly explore what the impact of an earthquake is on different kind of faults around it, because maybe strike-slip faults are inhibited and thrust faults are promoted, or depending on where you are, one's promoted and one's inhibited. Okay, so now let's show you how you can combine these stress patterns and all that other good stuff you created with your with active fault files and overlays and earthquakes. So what I'd like you to do now is to go to Input menu and open existing input file, and let's open the sfbay.mat file that you created earlier. If you can still find that. Yeah. Now, if you didn't create it, no big deal. You can just open the original sfbay file, and you can quickly add these things again. How many people didn't create it and want us to recreate it? Okay, so we'll just do that again. So Shinji's going to, for those of you who have it open, just sit there and, go from, no, that's, go input. existing. Yes. Example SF Bay Area is your input file. Okay. So now Shinji's going to add go get the coastline information. If you've already done this, you can just relax. Because if you have an MAT file open, you don't need to do this. If not, it's just practice. Okay.
Strange.
So it's readable. NCSN readable. Okay for everything. All right. So now we're back up. Everybody's got that up, hopefully. So now what I want you to do is go functions, stress, Coulomb stress change. Okay. And now let's just say fine for that specified fault direction. That's the direction of the green fault we have in there, that kind of Loma Prieta-ish thing. And we have stress calculated at 7.5 kilometers depth. That's about halfway down the fault. That's fine. And say Calcan view. All right, and now hit the interpolating button. And now let's make our earthquakes black so they're more visible. So to do that, we're going to go into Input, Preferences, Input menu, Preferences, and Earthquake, we're going to change those to 000, right, Shinji?
Yeah. Wow.
The RGB version of black. And make them the 10 is fine. And remember now we toggle them off and toggle them on to see that happen. Okay, so there they are. Are you there? Okay, now go to Functions. Actually, no, let's not do it that way. Let's go to the command, the Coulomb, the MATLAB command panel, and write in Coulomb _ 3D _ view. Coulomb, so now we're back at the command window, barking commands at it. Coulomb.
Something wrong with this.
_ 3D _ view. Yeah, there we go. And then click. Yeah, the command is Coulomb _ 3D _ view. And just so you know, in the table of contents of the manual, at the end of the table of contents is something called Plug-in Finder. So you can find all of these guys that we've given you, so don't worry about it. Okay, so now go back to the file that we created. And now with the swivel, just play with it. So now you've really been able to add all these things together and look at it in 3D. You can save this 3D version, or you can create any source you want and output it to a PDF file.
Forgot to mention that the red color on the source fault is not the stress increase. This is the
slip.
Yeah.
Yeah. In this 3D view, the source fault has its slip represented.
So
well, let's try functions 3D view then. Let's try that. Functions. So we're going to get out of the plug-in and just go to 3D view. All right, and that's without the stress in it. Okay, let's take a look at a couple of stress cross-sections now. And for that, we'll go to the input file, and we'll open the TH, that thrust earthquake input file we've used a bunch of times. So open existing input file. You guys got that? Okay. And now we're going to go functions, stress, Coulomb stress change, calc and view. And now what we're going to do is, let's see, what do we want? A cross-section in the lower left-hand corner of that stress control. We're going to choose cross-section. And it happened to have a cross-section in it, and just like the others, you could create one if you wanted to. But we'll just accept this and say calc and view. And so now let's slide that over the map so we can play with it a little bit more. No, other direction. So we can see the control panel. Okay, so now let's change that to interpolating and change it's a little oversaturated. So we want to do that for, yeah. And now let's change the saturation so it saturates at, no, the other direction. So it, yeah. And now let's look at the cross-section. Yeah. So this is how the cross-sections were made that you saw in the introduction. You can easily make them. The dashed line, again, is the depth at which the map is made at. You can see the relationship between AB and AB. And you can easily look through the fault. Shinji, why don't you make a cross-section just beyond the end of the fault?
Let's see. Here?
Yeah. Yeah. So there's that kind of the butterfly wing just beyond the end of the fault and its location. And, of course, you don't see the fault in there because we're not crossing the fault anymore. But you do see the A and B, and you see the depth slice. So, you know, and now make another one that goes right through it, parallel to strike.
Let's see.
No, go beyond the, yeah. Yeah. A little weird, but let's do it. Yeah, definitely weird. So anyway, you can explore this, and you can very quickly adjust the stress scaling so that you can see the details that matter to you.
Actually,
And you can superimpose aftershocks on these cross-sections as well. What were you going to
Yeah.
say? So it's just as easy to include that. Now, another thing that we often want to do, let's go back to the map view, close the cross-section, is notice, going back to that guide, that it has an option for depth range rather than just a fixed depth. Obviously, a fixed depth is just a slice through the thing, a horizontal slice on which we're calculating stress. But depth range gives us some other options that we find very useful. So click on depth range. And our thinking is that quite often what you really want to know is, for every position, you want to know the depth at which the maximum Coulomb stress is occurring. Because if you're assuming that aftershocks are occurring at every point along the fault on which the Coulomb stress is most positive, maybe they're also occurring at the depth at which it's most positive. So let's choose maximum values, and then it gives you a range. So let's make a more narrow range rather than, I don't know, 5 to 15. Now, you see how it has an increment there? So it's going to actually make 4 calculations, 5, 10, 5, 10, and 15. So let's change, yeah, you can just leave it as it is there. And now we'll say OK. And calc and view. And now it should be redder than what you're seeing right now. Because it's over those depths, it's finding and reporting the one that is the deepest. And if you output the numerical file will tell you at which depth each one of those is, if you want to know. But we often use a depth range rather than a particular depth. And as you know, after seismicity catalogs are often least accurate in depth. So 5 kilometers, 10 kilometers can be well within the uncertainty of the depth range. And the other option we didn't choose it, there's no need to, but it also has mean is the other choice. The difference is if you do a maximum depth range, it's going to be more red than it is blue. If you do mean, it's going to be equally red and blue, basically, because you're not hunting for the reddest depth at any point in the calculation.
This is mean.
That's what? That's mean. Yeah. Now, the other thing that I would like to show you is those principal axis that Steve asked earlier about the principal axis. So I'd like to plot principal axes. And so for that, let's go back to the left lateral case. So open existing input file, example 2LL again. Functions, and now to see this without it getting too crowded, let's change parameters. Functions, change parameters, grid size, and let's change that to 5 by 5 kilometers. Otherwise, things get kind of crowded. And then you have to go, grid 2D view again. Now go functions, stress, Coulomb stress change. All right. So now we're going to use for the first time that regional stress information, which is contained in the file. I'm going to choose optimum strike slip. In other words, we're finding for strike slip faults the optimum orientations. And we're going to choose strike line, which is the optimum planes. And let's choose interpolating. So now you can see that we have a right lateral, right lateral and a left lateral zone. And Shinji, why don't you zoom into kind of the upper quarter of that plot? Yeah. Notice that when you zoom in, this is just a really cool thing. When you zoom in, that legend stays there in the picture. You don't lose the legend. We didn't quite pull that off in the displacement vector legend, but Shinji did it, nailed it here. So first of all, you can see that the angle between the black and the gray lines is not 90 degrees because the friction is 0.4. If Shinji were to change the friction to be 0, then God willing, they'll be orthogonal.
Right.
I think so.
Well, how about the opposite case?
Yeah. Yeah, and now they have a more acute angle to each other. So this is saying that what we're expecting, if it's a right lateral fault rupture, it would be on the black plane, and if we're a left lateral rupture, it would be on the gray plane. And what you can see here is that it's red along the fault, but it's red along the fault for faults parallel, for right lateral faults parallel to the left lateral. So the source fault is left lateral. Where's my pointer? The source fault is left lateral, and see the black ones that are parallel to it? So that's saying, well, you would expect either right lateral faults on that or these very highly acute faults. And you might say, well, but does that really happen in an earthquake? Do we really get aftershocks very close to the fault on very, very different planes? And I think it's an open question. Geologists would tell you that fault zones are highly fractured and have all kinds of high angle, low angle secondary features. And the best kind of double difference work in focal mechanisms suggests that there's quite a diversity of focal mechanisms, even on a fault plane, in many but not all cases. Anyway, it's something that you can explore. So those are the optimum planes that are being calculated. And those optimum planes basically bisect the principal compression axis. And that principal compression axis, again, is the combination of the stress contributed by the earthquake and the regional stress. So let's look at the principal axes. Yes?
So, the color here refers to Coulomb stress change on right lateral or left lateral fault?
Okay, great question. It's exactly the same stress change on either of these planes as long as this one is a right lateral rupture and this one is a left lateral rupture. So it would be giving you that, but if it were on a different plane, then it would not be the right value of stress. But on these planes, the Coulomb stress change on these planes, that's both shear and normal, is identical.
Conjugate for.
Because they're conjugates. Yes. Jessica?
So, was there information on the regional stress in the input file that we wrote in?
Yes. So we will take a look at that regional stress. And so, in fact, Shinji, why don't you go to Functions? Tools. Everybody go to Functions, Tools, Principal Axis Calculator.
Most difficult part.
Yeah. Now, that actually is not the let's close this. Wait a minute. What I want to show them first is the current stress that's in there. So to do that, we go to Input, Open and Edit, right? Open and Edit Input File. And choose that same file we're using.
This one?
Example 2LL, yeah. And say Open. Okay. And now you can see the second box down is this regional stress that's been specified in this file. And
How about changing the 1,000?
let's not change it yet. Let's just talk about it. So we have S1, S2, and S3, the maximum principal compression axis, the least principal compression, and the intermediate. Intermediate is S2. And we originally built Coulomb, and it just had a uniaxial compression, and life was simple. But we fell for it. People said, oh, you know, that's such a naive version of the stress. So we built this bloody thing, and it now can have a vertical stress gradient, and it's a fully three-dimensional stress, and it's a monster. And I, in some ways, regret that we ever did it. But okay, it's there. And so what we have done is made it so that you can create your own regional stress, making sure that it meets the criteria, which is that all three principal axes must be mutually perpendicular. If you don't do that, then things get bad. And so the principal stress